Across Southeast Asia, there are megacities sinking fast. All face major climate challenges from rising seas, floods, and extreme weather events. The race is on to predict how fast cities will sink and how the changing ocean will impact their sustainability. The ocean is our planet's life support system. It regulates our climate, absorbing huge amounts of carbon dioxide from the atmosphere and providing us with vast stores of food. But the ocean is in trouble. Population growth, rapid infrastructure, climate change, and events happening far away in polar regions are impacting the ocean, affecting many aspects of life across Southeast Asia.
Southeast Asia has a very unique place in climate research and sea level science. We have the highest biodiversity in the marine and terrestrial realm on our very doorsteps. But we are also set to be one of the regions hardest hit by sea level rise.
Megacities like Jakarta, Manila and Ho Chi Minh City are sinking, in some places at alarming rates.
The connection between a healthy ocean and healthy people is nowhere more obvious than in Southeast Asia.
We have so much to learn, and we have so much to contribute to being part of the solutions for our changing oceans.
Travel with scientists from the Earth Observatory of Singapore across the region to understand what is causing cities to sink, how they're being monitored, and why building resilience into communities is critical to their long-term survival. Professor Emma Hill from the Earth Observatory of Singapore leads a team of researchers who are monitoring the rate cities are sinking around the world and here in Southeast Asia. And it's faster than you think.
Asia is home to over 4.5 billion people, and many of these people are living in coastal megacities. Worryingly, many of these cities are experiencing frequent and extreme climate events, such as floods, coastal inundation, and storm surges. These threats are compounded by sea level rise, urbanization, rapid infrastructure growth, and population growth. And on top of sea level rise due to climate change, megacities are sinking, in some places at alarming rates. But what is causing these cities to sink? This is one of the questions that drives my research team. How can we measure whether, and if so by how much, cities in the region are sinking? We need to use as many data as possible to build a predictive model so that communities and nature in the region can thrive.
At the Earth Observatory of Singapore, we are doing research to look at the fastest sinking cities in the world, and they are here in Southeast Asia. Cities like Jakarta, Ho Chi Minh City, and Yangon are in the top 3 with the fastest subsiding land. Across the world, there are other cities from the US to Europe which also experience land subsidence, but none are as fast as what we're seeing in the Southeast Asian region.
Jakarta, one of the top 3 cities, is buckling under the weight of its own rapid development. With a population of 11 million, it is one of the world's largest cities, and it is sinking fast.
If we look at the data, parts of Jakarta are sinking at more than 10 centimeters per year, maybe up to 20 centimeters per year in some areas. What is causing this sinking? This low-lying coastal city isn't only threatened by climate-related sea level rise, but it is also literally sinking into the ground. The reason is that water is being pumped out from natural aquifers below the ground to meet the water needs of the city's residents. When the water is pulled out from an aquifer, the sediments in the soil compress and the ground sinks. In places like Jakarta, we have land sinking and the sea surface rising, and together these relatively result in more rapid sea level rise. Other areas of Southeast Asia are seeing land height changes due to earthquakes and tectonics. Earthquakes and plate motion can actually change land heights all across the region. Thailand and Malaysia have seen significant land height changes due to the big sequence of Sumatran earthquakes that started in 2004. Even Singapore has lost a few centimeters of land height due to the earthquakes, and in the future it could lose more depending on the source location of the next earthquake.
To observe regional geohazard activities, a data hub has been established at the Center for Geohazard Observations at the Earth Observatory of Singapore to collect field data being recorded in the observation stations installed in collaboration with many universities and government agencies across the region.
We are now at the Center for Geohazard Observations. This is the place where we actively manage the many geostations that we have installed in our region. Working together with our overseas collaborators, EOS has over the years installed many geohazard observation stations in our region, in countries such as Indonesia, Myanmar, Bangladesh, India, Bhutan, Philippines. The Geohazard Observation Station comprises of GNSS station, seismic station, and volcano observation station. They collect geodetic and geophysical data that are transmitted back to a server, such that the scientists are able to use the data to discover more, uncover more about the geohazard and natural forces that is affecting our region. The newest observation station that we have installed is in Taiwan. It is installed in Kaohsiung. It is a GNSS station that observes the sea level change around the coast.
The data recorded and collected at these stations are sent back by mobile and satellite networks installed in geodata servers for scientific research.
Here we can see the tilt data that is recorded by our instruments installed at Gede and Merapi volcano in Indonesia, as well as Mayan volcano in Philippines. What you can see here are the seismic waves being sensed by our seismic station in Myanmar, as well as in the volcano in Indonesia and the Philippines. This wave is able to tell us when an earthquake has occurred and allow us to detect the parameters as well as the location of the earthquake.
Here at the Earth Observatory of Singapore, we're working with the latest technology to monitor and understand changes in both the height of the sea surface and changes in the height of the land. So we're watching cities like Jakarta, Manila, Bangkok, Ho Chi Minh City. These are all places that are experiencing subsidence due to withdrawal of the groundwater. And something that we can do in the future is combine the sea level rise that we expect because of this land height change with sea level rise that we expect due to climate change. And with those combined, look at how much we can expect coastal inundation and flooding in the future as a result. To process the huge volumes of satellite data needed to extensively survey the situation, we're collaborating with the NASA Jet Propulsion Lab to use a system they developed to handle the massive amounts of processing using a cloud computing environment. We need to look at the different pieces of the Earth system, in the ground, in the oceans, in the ice sheets and glaciers, and in the atmosphere in a holistic way. We need to understand the connected hazards that threaten the futures of cities and communities in Southeast Asia. If the sea surface rises or the land sinks, Either one will give you relative sea level rise, which is the difference between the sea surface and the land height. And relative sea level rise is what we really care about because we live on the land and care about where it sits relative to the sea surface.
We'll take this to the field.
It's pretty good. I like the concept, having everything inside a pelican case.
The technical team is preparing to install new monitoring systems to help track land movement and sea level rise to determine if Singapore is sinking, and if so, how fast.
Hello. How are things going?
Have a seat. I've got something to show you guys.
Great. We're wondering if we can get an update on the installation plans.
Yeah. Hey, recently I've done a 3D printing of a model of a possible GNSS station that we plan to install at Lazarus Island. In addition to having the necessary sensors and instruments that can record our data, I want to make the structure appealing, visually attractive, so that people can approach it and take a look. So the idea is that since the location is at the public area, right, if I can make it attractive like this, and then we have some infographic boards explaining to the public what exactly this installation is doing and the sea level rise research is investigating, I think it's a good opportunity to engage the public and to educate the public.
The ultimate goal is a more resilient community, and we're not going to get there unless everybody's on board and educated on the topic. So yeah, that's fantastic. I think we'll do everything. We'll do land height, sea level and water vapor, all from this one beautiful station. Very cool.
Water vapor is another critical element being monitored to understand the impact the changing ocean is having on storm intensity in Southeast Asia.
Recently, there have been a whole bunch of new, innovative advancements that mean we can use the same data from these GPS stations also to measure how much water vapor there is in the atmosphere, and if the station is near to the ocean, changes in the height of the sea surface. This map shows global positioning system, or GPS stations, that we have installed all around the region. They're continually fixed out there, measuring their position. So any changes in their position due to, for example, an earthquake will be recorded, and they can continually monitor changes in land height. And we're actually installing some of these soon on the coastlines of Singapore for the purpose of measuring both land height and sea surface changes.
The technical team are traveling to Lazarus Island. Here, they will survey the coastline for a good location to install a test station. As this is one of their new GNSS models, all functions need to be checked.
No, Lazarus Island, I think this...
Are there corals?
Yes, they are. They're quite a...
Let's go.
Okay.
Be careful.
Hi, Jeff. Hi,
Hi
Piso.
guys. How are you?
Nice to see you guys. Right, today we're going to set up a station for temporary survey. The key thing is to do a couple of days of data collection to assess the impact of a low tide situation, so that we know whether the location is a suitable one for a permanent station.
Lazarus Island sits in the Straits of Singapore. It is uninhabited, has a wide range of fauna and flora, and is a perfect location for scientific research on sea level rise and land height movement in the Singapore region.
Right, let's unload our equipment and check the equipment. Okay?
The GPS receiver we have already put here, solar panel controller, modem for data communication, I think, and also this is the timer. All cables connected.
And we also have done a check back in the lab.
Yeah.
Yeah, I think we should be good. All right, let's set this up and get the thing going.
The team checked data networks, satellite logs, and uplinks before setting the system live. They need to make sure the GPS signal can read a clear line to the sea surface at both high and low tide.
Yeah.
It's really important for us to determine the impact of the low tide
Yes.
on the signal.
Yeah.
What do you think is this situation now?
Yeah, I can see that currently the water level is a bit low than normal, so probably it's low tide and it's maybe still going down.
Shall we do some measurement? Be careful, be careful.
Yeah.
So Nudin, what's the distance now at this low tide position?
7 meters up here.
Okay, so it's 4 and 7.
7, yeah.
Okay. So we take note of these parameters and we go back to the office and do some computation
Yeah.
to ensure that we will mitigate or reduce as much risk as possible
Yes,
before
yeah.
we start the actual installation of the real thing.
Yes. Yeah.
Okay.
Armed with this knowledge, scientists and engineers can work together to find long-term solutions to monitor sea level rise and relative land height changes. But land height can also change very quickly.
Southeast Asia is surrounded by what we call the Southeast Asian Ring of Fire. That's this chain of volcanoes. There's 750 of them or more that are active or potentially active. And then these big tectonic plate bounding, earthquake generating faults. And these faults divide the tectonic plates, which are constantly moving relative to each other. Along the fault, the plates get stuck, so stress builds up between earthquakes, and then that stress is overcome very quickly, producing earthquakes.
An earthquake resulting from two tectonic plates colliding has the potential to rapidly move land height across the region. But by how much and how far is what scientists are trying to predict.
To understand where we might see land height changes resulting from earthquakes in the future, we need to know where the seismic gaps are in the region. So we can use this figure to talk about what a seismic gap is. What we have here is the Indo-Australian tectonic plate diving underneath of Sumatra, and it's doing this along what we call the Sunda megathrust. And this megathrust is where the earthquakes are produced. They happen when the two tectonic plates slip suddenly relative to each other along this megathrust. And what we've marked in pink here are the areas that have already slipped in the earthquake sequence that started in 2004. And what you have here that's not marked in pink is a seismic gap. It's the area of the megathrust that hasn't slipped in the last earthquake sequence. So we need to be worried about this. We can expect that this area may produce a large earthquake, and that can trigger a tsunami that would impact all the exposed coastlines around it. Singapore won't experience the tsunami, but this will also cause land height changes across the region, including potentially at Singapore. With all the different things that can affect land heights and sea surface heights, we're looking at a really dynamic picture with a lot of moving parts. To give some idea of what we're dealing with, the magnitude 9 earthquake that hit Japan in 2011 caused a huge tsunami, and it moved tectonic plates up to about 60 meters relative to each other along what we call the megathrust, the fault that divides the plates. That's a lot of movement. To help you imagine what 60 meters looks like, it's about 5 double-decker buses lined up in a row. Imagine the Earth's crust being displaced by that much in a matter of minutes. When that happens, the Earth's crust near to the fault buckles and reshapes, causing drops and rises in land height over a wide region.
Resilience is an important lens for urban planning. It is very relevant to a lot of the hazards and risks that need to be addressed for cities and communities that are being impacted by climate change across Southeast Asia.
So an important part of the solutions to building more resilient cities are what we call nature-based solutions. So nature-based solutions are actions that help manage or restore ecosystems, whether they are natural ecosystems or modified ecosystems, if we think about a green roof, for example. And all these nature-based solutions really help mitigating the risks, whether it is by reducing temperatures in cities, by providing shade, or infiltrating water to help reduce urban flood risk. Also coastal flood risk when we think about coastal ecosystems.
Here, on Cambridge Road in downtown Singapore, communities are trialing a resilient community project, building green spaces, shaded areas, and planting trees and grasses to reduce the impact of flooding.
It's an exciting project, it's growing well.
Yeah, it's changed so much since the last time we were here. You can really see what the community has done. So here on Cambridge Road, where we've launched this Resilient Community project, we've really made a point to get everyone in the community involved in solutions to extreme weather and climate change.
So the goal of this project is to build community resilience as a complement to infrastructure resilience. So by tackling both the hardware and software side, we truly build a resilient city. So if you see, the project is designed to bring the community together so that they can learn, share, and make good improvements in their neighborhood.
These very seemingly simple solutions like tree planting or the community garden that allow the community to come together and act cohesively, and at the same time, those same actions are increasing the capacity of the natural systems to absorb rainwater, and they're helping with mitigation to climate change by capturing and storing carbon dioxide.
To date, they have initiated over 17 projects. Some are completed, some are ongoing, and some are in the works.
Ensuring the future sustainability of cities and communities in our region is what drives my research team in the lab and in the field. We must do everything we can to understand the threats around us and how they connect and compound to create disasters. We need to measure changes in land heights, predict climate-related sea level rise, understand tectonic deformation of the Earth's crust. We need to do all these things so that we can inform policymakers and urban developers so that they can make more informed decisions about mitigation. We must build resilience into cities around the region to ensure our communities will remain sustainable in the face of sinking cities and changing oceans.